So, hello, I'm Hasan Qarehdaghi, and the title of my talk is Easy CDM, and it's based on a work supervised by Dr. Jamal Amanirad at Shahid Beheshti University in Iran. This talk is about fitting a model of continuous decision tasks to data. So I will first briefly talk about continuous decision-making tasks and circular diffusion model, and then introduce the method and illustrate its performance. And then I will talk about the robust version of this method. I think I should. How can I hide this? Okay. The continuous decision-making task. Decision-making was the subject of research for many years, but researchers most often use the decision-making in which the number of options were finite, mostly two options. But we can argue that there are benefits in using decision-making tasks in which there are a continuum of options to choose from. For example, the random dot motion task here, where the subject should decide what's the motion direction, coherent motion direction of some dots, either left or right. But we can argue that the motion is naturally a continuous type. In our daily life, our judgments about perceived motion direction could be in any angle. This is not just about motion, the speed of motion or the orientation of objects or color of objects or other features of, for example, visually perceived things could be continuous type, or more than that, more than perception. For example, the motory movement, for example, for reaching something they can, the brain should choose from a continuum options for adjusting the movement of fine muscles. So it seems that it's more natural to use continuous decision tasks in research, and also they seem to be more informative. When we use continuous version of this random dot motion task, for example, then we allow the dots to have a coherent movement direction in any angle and ask the subject to choose from any angle, we will get a distribution of choices over all possible angles instead of just one single number that shows the proportion of correct trials in the two choice action version of this test. So you will have more information that could give new insights about the underlying process. And evidence accumulation models is a class of models which model the time course of these decisions. The circular diffusion model here is a model for such continuous type decisions. For example, then we have a task in which the subject should remember the color of these squares here, and then should recall the color of the clothed item and choose from this circle representing all colors. The circular diffusion model models this procedure as the integration of information over time and the integrated information in any time is represented by a state point in the two-dimensional plane. And this evolves according to some noise captured by diffusion process, but also with some systematic tendency to move in one direction, represented by this drift direction, the direction of this drift vector. Also, the length of this drift vector represents the speed of this systematic change in a state point. And the decision is made when the state point reaches a threshold distance from the origin, represented by A, and the hit point represents the choice, and the time to hit plus non-decision time represents the response time of the subject in this trend. So if this model is correct, at least to a good approximation, we are interested in finding these four parameters of A, the angle of the drift vector and length of the drift vector, and the non-decision time. But we only have the behavioral data, the choices, the angles of chosen points in the trials, and also the response times. And we want to deduce the parameter values from these experimental data. And this is called the parameter estimation, the problem of estimating the proposed data generating parameter values. The common good method for estimation is maximum likelihood estimation, in which we try to find the parameter values which maximizes the probability of observing this experimental data. The likelihood function for the CDM is like this. Here, the A is threshold, V is the drift length, theta V is the drift angle, theta is the choice angle, T is response time, and T0 is non-decision time. I0 is I is the modified Bessel function, J is Bessel function, and this J is a zero Bessel function. We can write the likelihood function as the multiplication of two terms. The first term only depends on theta, not t, and the second only depends on t. So these two are marginal distributions of choice angle and response time, and we can see that these two are independent of each other. If you look at this first term, the marginal distribution of choice angle, it's a famous distribution called von Mises. The two parameters, mu as the mean of the distribution and kappa as the concentration parameter. Actually, there are the maximum likelihood estimates of this family of distributions should satisfy these two equations. Actually, the first right-hand side in the first equation is called the angular mean, and the second equation is called angular variance of the distribution in the orientational directional statistics. So we have two statistics to come to popular statistics here, and if we can use them to estimate the parameters. But here we have only two equations. If we want to estimate our four parameters, we should construct a system of four equations to be solvable for our four parameters. And we try to find two other equations. Our two other equations will come from the response time data. This is the marginal distribution of the response time data, and it is, again, a famous one, previously analyzed distribution, and is called the first distribution of first passage time of Bessel process with drift. Uh, we cannot estimate we have not formulas for estimating the maximum likelihood function here, as the formula is a bit complex. It's an infinite series and not well behaved, but there are other methods for estimating the parameters uh, instead of maximum likelihood estimation. One is called the method of moments. In this method, we built equations. In one side, we put the moments of the model, and the other side, we put the moments of the data. And we find the parameter values that solve the equations, which the moments of the model becomes equal to the moments of the data. Fortunately, we have a closed form of moment generating function of this distribution, which, as its name suggests, we can generate the moments easily from it, like this. So we could have two moments of the model and use it to build our two equations. But actually, the variance is more popular than the second moment. So we use variance instead of second moment and calculate the variance of distribution like this. So we now have our four equations. To review, to estimate the parameters, we only need to calculate the mean, the angular mean, and the variance of the choice angle data, and mean and variance of response time data, and put them on this system of equations. But we need to solve the system. The first equation in the system actually directly gives the vector angle of drift. And also the second equation varies only with A. So we can solve it for A. We can rewrite it as this. And 1 minus the angular variance actually is called mean resultant length. And here we can solve it for kappa. Kappa is AV, and there is a heuristic approximate solution for this, but it's not accurate enough for our use here. So we use a single iteration of Newton-Raphson, which just a single iteration gives a good approximation of kappa. So now we have kappa, and we can use the fourth equation. We can rewrite it as V and kappa and solve it for V, which yields this. And now that we have V and kappa, we can calculate A from them and use the third equation to calculate T0, as we have all other variables. So the easy CDM is just calculating mean and variance of choice angle and response time data and doing these calculations here, which gives the parameter values. Now let's see that how's the performance of this estimation. To test the performance of estimation, I compared the performance with the maximum likelihood estimation on the whole circular diffusion model. So I simulated data sets of 100 and 1,000 trials from a vast values of data generating parameter values. Here for drift length, I used 0.5 to 4.5 as drift length, which encompasses really good natural value that we may encounter in behavioral data. And then for each data set, I recovered the parameters using maximum likelihood or easy CDM, and each point here represents the estimated value against the data generating value of drift length for the maximum likelihood and easy CDM. And we can see that easy CDM is performed largely to maximum likelihood method. both in terms of bias and variability in the estimation. Also, this is a plot for the threshold, which also the performance is comparable. And this is the performance for drift angle. Actually, for drift angle, we do not need to vary the data generating parameter value, as we can see that looking at the formulas, we can see that maximum likelihood and easy CDM are not sensitive to this data generating value. So again, the performance is satisfactory, and this is for the non-decision time. Again, no need to vary the data generating value of non-decision time. The variability is a bit higher in the easy CDM. So this was the performance, but after I submitted the paper to COXI, I further analyzed this method and found out that this method is very sensitive to contaminant data. One problem in experimental data is that they almost always contain some contaminant data that are not generated from the desired task. For example, here I took the data in the previous analysis and added a uniformly distributed number from 0 to 2 seconds to 5% of trials in reaction time, response time data, and estimated the parameters. And here the red dots are the estimated parameters of the easy CDM, and black dots are the estimated parameter values for the maximum likelihood when fitted on the uncontaminated data before contamination. And looking at the results, we can see that the performance is bad for easy CDM. Variability is high, there is evident bias, and it's not very good. But trying to find the origin of this bad performance, we can see that it's originated in the statistics that are used for response time. We use the mean and variance of data, which are expectedly very sensitive to change in data, even single or some little proportion of data. But there are more robust statistics for central tendency, like median, or discrepancy, like interquartile range. So we tried to replace the mean and variance with some other statistics of data. If we suppose that our response time distribution is normal, we can think that the median is a good estimation for the mean of distribution. Also, the interquartile range will be constant factor of the standard deviation. So these two could be replace the mean and variance statistics. And we can calculate the other formulas in the easy CDM, just replacing the mean and variance of response time with these two statistics. And estimating the same data sets, we can see that now the results are much more better, much more satisfactory, and comparable even to the maximum likelihood estimation than estimated on the uncontaminated data. And that was it. Thank you for your attention and time.